Hey everyone, welcome back to Chem Story. Have you ever looked at one of those complicated ring structures and thought, how on earth am I supposed to name this? Well, by the end of today's lesson, you'll be able to do it instantly. That's exactly what we're going to master today. We're diving into how to name cycloalkanes using IUPAC rules. If you've already learned how to name regular alkanes, you're in luck, because naming cycloalkanes follows pretty similar rules. We'll walk through it step by step. Let's get started. First, let's go over the general format for naming cycloalkanes. The name usually follows a simple pattern: prefix, cyclo, parent, and suffix. The prefix tells us what substituents are attached to the ring and where they're located. The cyclo part just means the structure is cyclic, so it forms a closed ring instead of a straight chain. The parent tells us how many carbon atoms are in that ring, and the suffix defines the functional group. For cycloalkanes, that's usually ane, since we're only dealing with single bonds. Alright, now let's break it down, step by step. The first step in naming a cycloalkane is finding the parent chain. Most of the time, the ring itself is the parent. But if there's a longer carbon chain outside the ring, we have to compare the two. If the ring has more carbon atoms than the longest chain outside, we go with the ring as the parent. Even if the ring and the chain have the same number of carbons, the ring still takes priority. But if the chain outside the ring is longer, then the ring gets demoted to a substituent, and we name it as a cycloalkyl group. Looking at the first image, we can see an example of these rules in action. In the example on the left, the ring is bigger than the attached chain, so the ring wins and becomes the parent. That means the chain is just a substituent. But on the right, it's the other way around. The longest continuous chain outside the ring has more carbon atoms than the ring. So in that case, the chain becomes the parent, and the ring is named as a cycloalkyl substituent. And that confirms our rule. When the chain is longer than the ring gets downgraded to a substituent. In this example, the ring is the parent, not because it has more carbon atoms, but because it ties with the longest continuous chain outside the ring. According to IUPAC naming rules, when the ring and the longest chain have the same number of carbon atoms, the ring always gets priority. This rule keeps naming consistent and helps us prioritize cyclic structures when they're equivalent to straight chains. Once we've decided that the ring is the parent chain, the next step is to number the carbon atoms in the ring. The goal here is simple. We want to number it in a way that gives the substituents the lowest possible numbers. Let's say we have a cyclohexane ring with a single methyl group attached. In that case, it's super easy. The carbon with the substituent automatically becomes carbon 1, so we don't even need to mention the number. But what if there's more than one substituent? That's when we need a clear set of numbering rules. If the ring has 2 or more substituents, we need to number the carbons so that the substituents get the lowest possible numbers. We always start numbering from the substituent that gives the smallest number at the first point of difference. And if there's more than one possible way to number it, we choose the set of numbers that's lower overall. Halogen substituents, like chlorine, bromine, or iodine, follow the same rules as alkyl groups when it comes to numbering. Let's go through some examples and see how this rule works in action. Let's take a look at the 3 structures. In the first one on the left, we number the ring clockwise. That gives us substituents at positions 1, 3, and 4. In the second structure, we also go clockwise, but this time we get 1, 2, and 5. In the third one on the right, we switch directions and number it counterclockwise. That gives us 1, 2, and 4, the lowest possible set of numbers. Comparing these results, we can see that the structure on the right matches the IUPAC convention best because it gives the lowest possible set of numbers for the substituents. So 1, 2, and 4 is the correct way to number them. But what if 2 different numbering methods give us the exact same set of numbers? Well, that actually happens sometimes. And when it does, we use alphabetical order to decide which substituent should get the lower number. Let's look at an example. In the first structure, we start numbering from the methyl group, so it goes on carbon 1, and the ethyl group ends up on carbon 3. In the second structure, we reverse the numbering. This time, the ethyl group is at carbon 1, and the methyl group is at carbon 3. Both give us the same positions, 1 and 3. So in this case, we apply the alphabetical rule. Since E comes before M in the alphabet, ethyl gets assigned to carbon 1, and methyl goes to carbon 3. That way, the naming stays consistent and easier to follow. Once we've numbered the ring, the rest is just like naming straight-chain alkanes. We figure out what each substituent is and assign a number based on where it's attached. Then we list all the substituents in alphabetical order when we write out the full name. The last step? Just put everything together into one single word. If there are multiple substituents, list them in alphabetical order, but ignore prefixes like di, tri, and tetra. And finally, the name of the parent cycloalkane goes at the end. And that's it! Naming cycloalkanes really just comes down to 4 simple steps. First step, find the parent chain. The ring is usually the parent, unless there's a longer chain outside the ring that takes priority. Next, number the ring correctly. Start at the substituent that gives you the lowest possible numbers. Then, list the substituents in order. Remember, we go by alphabetical order, but we ignore prefixes like di, tri, and tetra. Finally, put everything together into one name, with the parent cycloalkane name at the end. At first, it might seem a little tricky, but trust me, with just a bit of practice, it'll feel like second nature. Now it's time to test what we've learned. Thanks for watching, and I'll see you in the next video.